Let's take a look at sigma x distribution that we get from answers. So in solution, highlight sigma x in the tree, and let's start with the default view along the z-axis. So if I go and click on z here, I'll get the default view, and let me zoom out a little bit. So I can do that using the middle mouse wheel. Okay, and note that the model, the displacements are, the deformed shape is scaled by a factor of 32 so that you can actually see the deformed shape, and the black line shows the undeformed. Now if I change this to true scale, so show the deformations on true scale, you can see you can hardly see the deformations. And while viewing the stresses, I actually, at least for a linear case, I prefer to just turn off the deformation. So I'll go here and just turn off the deformations, and that's like a personal preference. So let's investigate sigma x in the model. So click on probe, and let's first investigate sigma x kind of in the center, away from the boundaries. So over here, if I move around, I see that I have around 200 megapascals. So over here, in the center, it's really close to 200 megapascals, and I've changed my units to megapascals by going here, and so that agrees with our hand calculations. Voila, yippee! So that's one good thing. Now let's investigate sigma x at the boundaries, and first let me look at the top and the bottom boundaries, and here again I see that sigma x is pretty close to 200 megapascals, and that's what so here the traction boundary condition doesn't affect sigma x because sigma x doesn't act on the free surface at that boundary. So okay, that's boundary condition agrees with what we expect. What about at the right boundary? Okay, over here we can see that we get a huge stress right where the point load is applied and around it, and that is to be expected. In fact, as you refine the mesh, this value will go higher. Let me zoom into the right boundary. Now what about if I move away from that? Okay, you see that the traction becomes, sigma x becomes very small, because according to the traction boundary condition, it has to become very small because sigma x acts on the free boundary, at free surface right at that boundary. Okay, and that actually, if you look back at the tutorial, that agrees, so this is in the pre-analysis section, that agrees with what we expect, right? So we are specifying the traction at a point, and in fact that's infinite, but away from there the traction is 0 because those points are free to move however they can. And this view agrees with that. In fact, you can get that you can see that variation a little bit better if you change the scale here. You can't change the maximum, but you can change the value next to it. So double click on that and let me change that to 250, and let me also change the minimum, and again I can't change the lowest, but I can change the value next to it, and let me change that to -50 megapascals, and voila, you see this actually stuff happening here that now comes out. And so again with probe, so I have 200, and then it decreases sigma x and then becomes 0 at the boundary, and so that's expected, right? So 200 here, and as we move here, it goes to, sigma x goes to 0 because this boundary condition affects sigma x. Okay, what else? Let's take a look at the left boundary. I can go back to the previous view by clicking here and probe what's happening at the left boundary. And you may have to translate it a little bit. If the left boundary is too close to the color scale, the probe values won't apply. So click on probe, and I see that the value is close to 200 megapascals, but it's a little lower. That's the effect of constraining it. But then over here, it becomes very high. In fact, you can see there's like a concentration here. And as I refine the mesh, that value will keep getting, at the corner, will keep getting higher and higher because it's infinite. You have an infinitely sharp corner constrained. The stress is infinite, and we can get rid of that by filleting the corner. Okay. We check the boundaries, and if you want to reset the scale to the default, you can just click anywhere on the scale and reset all, and you'll get the default view. Okay, and if you're probing something and you click on the model, it'll put the value in there, and sometimes you just want to get rid of that label, and that's non-intuitive. To get rid of the label, you have to highlight this thing here, label, click on the label, and hit delete. So to summarize then, sigma x agrees with the hand calculation, in the middle and at the top and the right bottom boundaries as expected. And as I move to the right, I get zero traction here, which agrees with the boundary. I get zero sigma x here, which agrees with the boundary condition. I get a huge sigma x here, which again agrees with the boundary condition.